Hi everybody, so this is a video about the parts of the atom. So part of this I'll be able to go through pretty quickly because I have a feeling that you know much of this from before. So let's see. So what we're going to do is we're going to look at the subatomic particles and look at them in terms of their charge and their mass, and then talk about what is the structure of the atom and look at the subatomic particles. So I think we've talked about this enough. Atoms, of course, they're the smallest part of matter, and they're the smallest part to which an element can be divided, but yet still be called that element. And of course, atoms are the building blocks of everything. So atoms consist, though, of even smaller particles, because we talked about Democritus and we talked about Dalton, and we said that they thought that atoms were indivisible, but it turns out that that's incorrect. We know that there are smaller particles, including protons, neutrons, electrons, and then there's something called quarks, and then there's something called the Higgs boson. So you guys are really only responsible for knowing about protons, neutrons, and electrons, but I thought that it might be worthwhile to show you a little bit about quarks and the Higgs boson as well. Okay, so this is supposed to be an artist's rendering of what that electron cloud model looks like. So each one of those little dots is not an electron, but it's like one of the positions where the probability of an electron is high, where it could possibly exist. So we have the nucleus, and inside the nucleus we have the protons and we have the neutrons. So we know that that part, the nucleus, is really dense. It contains almost all of the mass. And then we have the electrons somewhere out there in the electron cloud. So specifically the protons, if you ever get protons, neutrons, and electrons confused, you can always remember that the protons are the positive ones. They both start with P. It's located in the nucleus, and it has a mass of 1 atomic mass unit, or called an AMU. And we will talk later about how the AMU unit came to be, but for now you can think of it as 1/12 of a carbon atom's mass. Okay, so we have the neutrons. The neutrons get their name because they are neutral. They're also located in the nucleus. They have, of course, no charge, and they also have a mass of 1 AMU. So now we have protons and neutrons both having the same mass, 1 AMU. And then, of course, we have our electrons. So up there at the top, we have some sort of a Bohr model representing some sort of atom. We know that our electrons are found outside of the nucleus in these things called the electron cloud. And we will talk more specifically about how the electron clouds are organized coming up soon. So those electrons are negatively charged, and they have a mass of almost 0. If you remember that when Thomson found the electron, he found that it was about 1/2000th of the mass of a hydrogen atom. So we know it has to have some mass because it's matter, so it has to have mass, but it's so small that for you and I, we can say the mass is basically 0. So if you think about the number of electrons and the number of protons, they have to cancel each other out in a neutral atom. So the number of positive equal the number of electrons, therefore the mass is 0. I'm sorry, not the mass, the charge is 0. So the next subatomic particle is the quark. And after you finish watching this presentation, I have attached a video that you can watch at the end that will tell you a little bit more about what a quark is. So what I can tell you about a quark is that they are smaller particles that make up protons and neutrons. So I know this is another one of those cases where you probably think, well, I thought a proton and neutron were the smallest particles that there could be. But it turns out, in fact, that a proton is made of 2 up quarks and 1 down quark, and a neutron is made of 2 down quarks and 1 up quark. So in that way, you can still think about protons and neutrons exactly the same, but now we just have them being made of smaller particles. So I didn't even cover the Higgs boson, and part of the reason that I didn't do that is because the Higgs boson is one of those concepts that's kind of hard to understand. So I also attached a video for you guys to check out where Hank Green tries to describe a little bit more what the Higgs boson is, just so that you can have some kind of explanation about what a Higgs boson is. But as I said in the beginning, you are really only responsible for knowing electrons, protons, and neutrons. So here they are, all in a neat little chart. So the electron, our symbol for the electron is lowercase e with a negative sign next to it. It has a relative charge of -1, and for you and I, we say that the mass is 0. Now, of course, if you look in the true mass, yes, it has a mass because we know it's matter. But again, it's so small to you and I, it just doesn't really matter. Then we have the proton. The symbol for the proton is a P with a plus sign. Oftentimes you'll see me write it just as a plus sign. The relative charge is +1, and the mass number is 1. And then finally we have the neutron. So that we write the neutron as a lowercase n with a not symbol, superscript there. The charge of a neutron is, of course, 0, and the mass number is 1. So again, I said I would explain what that atomic mass unit is. So an atomic mass unit is just another unit of measure for mass. And we use it when we need to talk about the mass of really, really small things. So an AMU is defined by looking at a carbon-12 atom. So what scientists decided to do was take a carbon-12 atom, determine what its mass was, divide it evenly by 12, and say, okay, that is what 1 AMU will be. And that value is 1.67 times 10 to the -27th kilograms. So yeah, that's pretty small. Okay, so I want to talk about one other little topic, and it is still related to those subatomic particles, because I want to talk about what the atomic number is and how it relates to how we identify an atom, talk about the term isotope, and then we'll get into looking at some atomic masses and looking at the number of electrons, protons, and neutrons in an atom. Okay, so first, you know that I love the periodic table because the periodic table can give us so much great information. But one of the most important things that you can get from the periodic table is the atomic number. So that is the big number that is at the top of each one of the blocks on the periodic table. And what the atomic number is the number that tells you how many protons are in the nucleus of each atom of that element. So if you look at carbon, you see its atomic number 6, therefore it has 6 protons. If you pick any other element from the periodic table, look at that number, and you'll know exactly how many protons it has. And so the atomic number and the number of protons is what's important to distinguish one element from another. So what is an isotope then? So we know that there are atoms of the same element that can have different masses. And the reason that they have different masses is that they have the same number of protons, the same number of electrons, but they have a different number of neutrons. And some of those isotopes are very stable, and some of them are radioactive, meaning that they are less stable. So I like to consider, when I talk about isotopes, what is the purpose of a neutron? And I like to think of the neutron as kind of this nuclear cushion Because if you think about how dense the nucleus is, we know we have all of these protons that are pressed really, really close together, and all of those protons are positively charged. So how do we get them so close together? Well, if we put some neutrons in there, they kind of help to buffer some of that positive repulsion that you might feel from having those protons so close together. So when we talk about whether an isotope will be stable or whether it will be something that's unstable in radioactive, kind of depends on the number of neutrons and if the atom kind of develops some sort of comfort level with the number of neutrons it has. If it turns out that the number of neutrons balances well with the protons, we get something that's stable. Otherwise, we get something unstable, radioactive, and it will break down and continue to break down until it gets to something that is a stable nuclear configuration. Okay, so how do you figure out how many neutrons something has? So if you use this equation here, you can see that if we take the atomic mass, so we can get that from the periodic table, and we subtract the atomic number, or the number of protons, what will be left is the number of neutrons. Because remember, all the mass comes from protons and neutrons. They both weigh 1. So if we subtract the atomic number from the atomic mass, we should be able to get the number of neutrons. So it becomes fairly simple arithmetic to get the number of neutrons. So now I'd like to show you an example of an isotope. This example is of hydrogen. So we know that hydrogen has 1 proton. And if you look at the example of hydrogen 1 there, you can see it has 1 proton there in the nucleus, and it has 1 little blue electron circling around it. But there are other isotopes of hydrogen. So normal hydrogen is hydrogen 1, but then if you go to the next hydrogen, that are hydrogen 2, that's called deuterium. And deuterium is fairly stable, and how deuterium is different from hydrogen is it still has 1 proton, but now the nucleus also contains 1 neutron. So the mass of that hydrogen atom would be 1 proton plus 1 neutron, which would equal 2. And yet there is yet another kind of hydrogen, and that is called tritium, and that's hydrogen 3. And tritium is highly radioactive, so that means it breaks down, telling us that the combination in the nucleus is not something that is really, it's not a stable configuration, so it breaks down. And what happens is we have 1 proton and 2 neutrons in hydrogen 3. So all 3 of these things are hydrogen. They are just isotopes because they have a different number of neutrons. So there are a couple different ways that you can write isotopes. So one really easy way is to just write the name of the element followed by the mass number. So carbon 14, carbon 12, uranium 235. And then we can also write it by composition of the nucleus. And so we write the element symbol from the periodic table, and at the top in superscript goes the mass number, and on the bottom goes the number of protons. So that here, this breaks it down to show you a little more clearly. So when you are writing isotopes in this form, what you want to do is have the X will be your element symbol. The A will be the number of protons and neutrons, or your mass number. And then Z is going to be the number of protons. And so if you needed to find the number of neutrons, you would take the mass number and subtract the protons, and then you would end up with the number of neutrons. So we can use that isotope format to look at another isotope, this time of uranium, and we can use the numbers that we are given to fill in the chart below so we can figure out how many number of protons and how many number of neutrons that we have. So by first looking at this, we know that this is uranium, and we can figure out either by looking at the periodic table that uranium has 92 protons. So let's fill that in. Okay, so we have uranium having 92 protons. And if you remember from the previous slide, we looked at that A and Z version of isotope writing. We know that Z also equals the number of protons, so we can fill that in as well. Okay, so we have Z filled in, and so we know the number of protons, and we know the number of protons is equal to Z. So now we can fill in the number for A. So A is going to be equal to the atomic mass. That is always going to be that superscript number in the isotope format. So for the one on the left, we have 235, and for the one on the right, we have 238. So let's fill that in. Once we have both A and Z filled in, then we're able to figure out how many neutrons something has. So remember that the number of neutrons comes from A minus Z, or the atomic mass minus the number of protons. So for the one on the left, that would be 235 minus 92, and that would give us 143 neutrons. And if we look at the one on the right, it would be 238 minus 92, which would give us 146 neutrons. So when you write things out like this, it's clear to see, yes, they're both uranium, they have the same number of protons, they have a different mass, and that different mass comes from having a different number of neutrons. So I hope this helped you understand the parts of the atom, where they belong, and how to look at isotopes. So if you want more information on quarks and the Higgs boson, check out the other videos that I've attached.